Hey everyone, and welcome back again to Star Studies. In this fourth episode, we'll basically be going over cluster membership of stars, and you'll know what I mean by that in a minute. And we're going to start by considering an interesting situation that will illustrate the very important concept behind this episode. Suppose that you have a large orchard of apple trees, and you need to find out what section of the orchard has the soil that's best for growing really red apples. You don't want just mildly red or yellow or any other type of apple. You want red apples. So you planted all of these trees many years ago and have raised them all since then. But something that you don't know is that someone came in right after you planted all of these apple trees and planted a few orange trees in the far side of the orchard. With no knowledge of these orange trees growing with your apple trees, you pick a year to do your research. You assign someone to harvest your orchard one section at a time, and you calculate what percentage of the harvested fruit for that section passes your test for being red. And after analyzing the results, you conclude that the ground on the far side of the orchard isn't good for growing red apples because there was such a low percentage of the harvest that turned out red. But in reality, you reached an incorrect scientific conclusion there. All of the orchard soil is good for growing red apples, and the only reason the far side didn't appear to be that way is because the oranges were included in our study. And in the end, that led to an incorrect scientific conclusion. So, the moral of the story is you can't compare apples to oranges. You can't compare apples to oranges, because if you do, you will very likely reach an incorrect conclusion in the end. And that is not what we want to do in scientific research. Now, in my research, we're not studying apples, we're studying stars. And you'll recall from episode 1 that we're studying stars in the open cluster M67. But the apples in my study are stars that actually belong to the cluster. And the oranges are stars that might seem like they belong, but really aren't true members of the cluster. Some of these stars that don't belong are actually much closer to us than the cluster itself, and we call those foreground stars. And other stars are much further away from us than the cluster, and we call those background stars. And these stars only appear to be in the cluster because they are in the same location of the sky as seen from our perspective from Earth. So we need a way to find which stars are actually real members of the cluster M67 and eliminate the stars that aren't. But when you look at M67 here, how can we tell which stars are members and which ones are not? I mean, can you look at this picture and tell me which stars belong to the cluster and which ones don't? It's not too hard to tell that some stars are brighter than others, and some are different colors than others, but neither of those characteristics of stars have to do with whether they are true members of a star cluster. So, how can we tell? And the answer is, we can use the spectrum of each star. And to see how we do this, we need to go over a little more physics about light. As we discussed in the previous episodes, light is a wave and has a wavelength. And when the source of the light is actually moving, whether that's a flashlight or a star, that affects the wavelength of the light that we see. If the object's moving away from you, it causes the wave to be stretched out, and the wavelength increases which makes it look more red. And if the object's moving towards you, that causes the wave to be squished, and the wavelength decreases, which makes the light look more blue. And this is what's called the Doppler effect, named after Christian Doppler, who I actually happen to share the same birthday with. And this effect is actually pretty easy to demonstrate with sound, which is also a wave. Now with sound, the wavelength corresponds to the note or pitch that you hear. So I'm going to quickly demonstrate this here for you with a car horn. Did you notice that right as the car passed by, that the sound coming from the horn dropped to a lower pitch? That is the Doppler effect. And it happens because the sound waves coming from the car switched from being squished to being stretched out. And that happens because the car switched from coming towards us to going away from us. And light waves behave this exact same way. It's just harder to demonstrate it because light travels so much faster than sound. But if you could travel fast enough, you could make the light from an orange flashlight appear red to an observer. And since everything in space is moving, the light that these objects give off experiences the Doppler effect. And the faster it's moving towards or away from us, the greater this Doppler effect is. So what exactly would the Doppler effect look like in a star's spectrum? Well, it would look something like this. The red dashed spectrum that you see here represents the spectrum of a star that is not moving towards or away from us, kind of like the sun. And the solid blue spectrum represents the spectrum of a star in the cluster M67. Now, in the last episode, I explained what these dips are that you're seeing and what causes them. And you'll remember that the wavelengths that these dips happen at are very well defined with quantum mechanics. But you'll notice that the solid blue spectrum appears to be shifted towards the right a little bit, which basically means that these dips appear to be occurring at wavelengths that are a little bit larger than what we expect. And that is because the light given off by the star got stretched out a little bit, like we just talked about, causing the wavelengths to increase by a small amount. And that's the Doppler effect taking place because the star is moving away from us at some specific speed. And we can actually measure how much the blue spectrum has been shifted and use that to determine how fast the star must be moving away from us. But how does knowing how fast a star is moving away from us help in determining which stars belong to a cluster? Well, you'll remember from the first episode that I compared a cluster of stars to a swarm of bees. All the stars are located relatively close to each other and are moving together through space. So we can use how fast the star is moving away from us, together with the star's location in the sky, and together determine how likely it is to be a true member of the cluster by comparing it to all the other stars. And that's exactly what we did with the stars that Apogee observed in M67. We took each spectrum and found out how fast it is traveling away from us, and if that speed was similar enough to the majority of the rest of the stars and was located pretty close to the center of the cluster, then it is very likely to be a true member of the cluster. And that is how we were able to make sure that in our research we didn't start comparing apples to oranges. So, I hope you've enjoyed this episode of Star Studies. The concept of not comparing apples to oranges that I've explained here is a very general concept that should basically be a part of every scientific study. And I've told you how we incorporated it into my research here. In the next episodes, I'll be explaining a couple other steps that we used in determining which stars we decided to use in our research. So, may the force be with you, and I will see you next time on Star Studies.